Working through some more further stats 1 revision now, we're going to take a look at the Poisson distribution. So we're going to look at some of the exam questions from the further stats 1 textbook, and we've even included an old question off the Edexcel, the original spec for further maths. Okay, so let's have a look at these questions. We've got a mix of things. I've started off quite nice, just looking at basic probability solving questions. So remember, if you're unsure, a lot of these questions won't actually tell you what distribution you're using. Now, Poisson, there's a big giveaway with it, and that is that it'll say it occurs at a certain rate. So in this one here, like we can see, the accidents occur at a rate of 0.7 per month. So it's always something per time frame. So it might be per hour, per 10 minutes, per month, per year. So it's always by a time frame. So let's get my pen. We've got a mean here of 0.7 per month. So question 1, my lambda is 0.7. Now, part A just wants us to find the probability of no accidents in the next month. Now, you've always got to check whether you've got to adjust your lambda. Because we're just talking about the next month, so a per month period, we don't have to change anything. But if you look at part B here, for example, we're going to have to adjust it. Now, the probability that there's no accidents in the next month, that'll be the probability that X is equal to exactly 0, no accidents. So, for these questions, I've calculated these on a graphical calculator. You need it if you're doing further stats 1, it really is an essential thing, but you can just use the formula for these as well. So if you do it with the formula, obviously you will be showing working, but you are allowed to just write the probability that X equals 0 and then write the probability. So in this case, the three significant figures, it'll be 0.497. Okay, so that's the probability that there's no accidents in the next month. The probability that there's exactly 2 accidents, well, in the next 3-month period, so we're going to have to adjust that. So 1 month is 0.7. So for this one, my lambda will be 0.7 times 3, so it'll be 2.1. Okay. And then we're going to calculate again, but X equals 2, because we want exactly 2 accidents. Again, I've just used a calculator for this. I'd recommend the same for you. This will give you 0.270. So again, 3 significant figures. And then finally, it says that there's no accidents in exactly 2 of the next 6 months. Now, this can sometimes throw people off a little bit. The way to think about this is if you're looking at a Poisson distribution, but over an extended time frame, and you're looking for a certain amount out of that period, that we don't model this with a Poisson, we model this actually with a binomial distribution. So, what I'm going to say is that X is modelled with a binomial distribution. Now, if it's 6 months, that means my n has to be 6, because we're looking over a 6-month period. Now, what's the probability that there's no accidents in 1 month? Well, we calculate that in part A, and often with these questions, they'll kind of build up to this. So like they've done here, we need to use the answer to part A. So my probability in part A was 0.497. So again, we're going to use that, 0.497. And then what we're going to do is use the binomial distribution on the calculator to calculate this. But what we're looking for, again, is the probability that X is equal to 2. Using this distribution here, X equals. So plug this on your calculator, and what you'll get is 0.238. Okay? And that's that question done. So be very careful with part C. This is very common. You'll need to normally use binomial for one of these questions where it's looking over an extended time frame. Okay, so binomial for the last one. But other than that, that was quite a nice introduction. It's not meant to be too difficult. So let's move on to the next one. The next one again is from mixed exercise 2 as well. This is question 3 though. We've got a random variable y, which is modelled with a Poisson distribution, and I've got this mean of lambda here. It says find the value of lambda such that the probability that y equals 5 is 1.25 times the value of the probability that y equals 3. Now for this, obviously we can't do this on the calculator, so you will need to use the formula for this. So it is worth being somewhat confident with the formula, but I'd still recommend you calculate anyway, for like we just did with the previous one. Just calculating them, it's dead quick. But for this we need the formula. So if you're unsure what the formula is, remember if X is modelled with a Poisson of lambda there, my probability that X to little x, that will be e to the minus lambda times lambda to the x all over x factorial. Okay. So we can use this information now. What we know is that the probability of y equals 5 is 1.25 times the probability that y equals 3. So in other words, if I write this down in mathematical notation, this is the probability that y equals 5 is equal to 1.25 times the probability that y is equal to 3. Okay. So let's change this now into the notation here. So this will be e to the minus lambda, because we don't know what lambda is in our case, same here, times lambda to my little x, which is 5, so lambda to the 5. And this is all over my little x factorial, so 5 factorial. This is going to be equal to 1.25 times, do it all in a big bracket, e to minus lambda again, lambda cubed this time, because this is the probability that y is equal to 3, lambda cubed over 3 factorial. So now at this point, there's not really any stats involved, it's just algebraic manipulation. What I'm going to do is I'm going to write out my factorials what they're worth, so that's e to minus lambda times lambda to the 5 over 120. That's equal to 1.25 times e to minus lambda, lambda cubed over 3 factorial, which is 6. Okay. And I'm just going to start solving here now and simplifying. So this 1.25 divided by the 6 here, I can write this as 5 over 24. So I'm going to do that just to make life a little bit easier. So this is going to be 5 over 24. So e to minus lambda times lambda to the 5 over 120 is equal to 5 over 24 e to minus lambda, lambda cubed. Okay. Here now, I can times through by 120. So if I do times through by 120, obviously my left-hand side would just be e to minus lambda times lambda to the 5. And then 5 over 24, if you times that by 120, that'll just give you, so let's just double check that, 5 over 24 times 120, that'll give you 25. So, timing through by 120 now, I get e to minus lambda times lambda to the 5 is equal to 25 lots of e to the minus lambda, lambda cubed. Okay. Now, what we're looking for is the value of lambda. So what we're hoping for here is that we can cancel this down to be lambda equals at some point. Now, looking at both sides here, we've got an e to the minus lambda on the left-hand side, we've got an e to the minus lambda on the right-hand side. And I've got lambda to the 5 on the left-hand side, lambda cubed on the right-hand side. So I'm going to look to cancel now. Now, the first thing is I can divide by e to the minus lambda, because you should be well aware of the fact that e to the x, or minus x in this case, equals 0, doesn't have any solutions. We can't find a solution for that. So we can divide through because it can be never equal to 0, so we're not going to lose any solutions. So I can divide by e to the minus lambda. So what that'll give me is lambda to the 5 is equal to 25 lambda cubed. Okay. Now, I can divide through by lambda cubed, okay? And if I divide through by lambda cubed, and we know we can divide through by this as well, because you should be aware of the fact, again, that when dealing with a Poisson distribution, the lambda value, so lambda, has to be greater than 0, okay? So you're not going to lose any solutions because it can never be equal to 0. So you can divide through by lambda cubed. So lambda to the 5 divided by lambda cubed, that'll give me lambda squared, and then 25 lambda cubed divided by lambda cubed, that'll just be 25. So lambda squared is equal to 25, so therefore I can take the square root here, and like we've just said, lambda has to be greater than 0, so we omit the negative solution, so that just has to be equal to 5. Okay, and that's simply it. My lambda value here is equal to 5, which gives me this expression here. Okay, so 3 marks for that. It's just the algebraic manipulation that makes that question more difficult than it needs to be, but in terms of actually setting the equations up, nothing too tricky. But there we have it, so that's that question done. The next one is another question here, but this time we're looking at combining Poisson distributions. So we've got internal calls coming in at a rate of 1 every 5 minutes, and then external calls at a rate of 2 every 5 minutes. So 3 parts to this. So part A, we're looking for the probability that the total number of calls is 3 in a 4-minute period. So I'm going to define both of these. So I is modelled with a Poisson distribution. So I is what I'm going to say is my internal call, so that's a rate of 1 every 5 minutes. And we're going to have the external be model with a Poisson distribution, and that's at a rate of 2 every 5 minutes. Okay. So combining these, because that's what we're looking for, the total number of calls, I can combine these. So I plus E can be modelled with a Poisson. Remember, we just add the two constants here, so it'll be 1 plus 2, giving me a value of 3 there. And that's every 5 minutes. So every 5 mins. So for part A, we're looking that the total number of calls is 3 in a 4-minute period. So like we said with the first question we did, we've got to always look to adjust this. So we want the probability that the total number of calls is 3 in a 4-minute period. So the probability that X is equal to 3. But first, let's adjust this. So this is for a 5-minute period. So what I can do is divide it by 5 and then times it by 4 to give me 4 minutes. So that'll be 3 over 5 times that by 4. That's going to give me 12 over 5. So that would be equal to 2.4. So lambda is equal to 2.4 for this one. So all you've got to do now is plug this in on your calculator. So it'll be the PPD function. This will just give you now 0.209. Okay, so that's your first 2 marks for question A here. So I've combined my Poisson distributions, worked out this. This is for 4 minutes. So that's that lambda value there. So part B, we're looking for the probability that there is at least 2 in a 2-minute period. So at least 2. So be careful which way you get your inequality here. That's the probability that X, if it's at least 2, we need greater than or equal to 2 in a 2-minute period. So 2-minute period, we need to adjust our lambda value. So 3/5 is 1 minute, so I just need to times that by 2, so that would be 3 over 5 times by 2, giving me 6 over 5. Okay, or that would be 1.2. So 1.2, so lambda is 1.2. So remember, if it's greater than or equal, we need to do 1 minus everything lower than that. So probably that X is less than or equal to 1. And to get this value here, this probability, I'm just going to plug it in on my calculator. So it's going to be 1 minus 0.66263. Do this on your calculator, you're going to get 0.337 to 3 significant figures. Okay, so that's part B. And then part C, we're looking for the probability that there's no more than 5 in a 10-minute period. So I'm just going to rub out a little bit of this above, just so I've got enough room. So if we erase all this, erase this as well. So we know our combined already. So we want no more than 5 in a 10-minute period. So I'll change that to C now. So no more than 5, so that is the same as doing the probability that X is less than or equal to 5. So it can be 5, but no more than 5. So that's got to be the probability that X is less than or equal to 5. And it's in a 10-minute period. Well, we know that the combined value for every 5 minutes was P out of 3, Poisson distribution with a mean of 3. So if that was for 5 minutes, I just need to times that by 2. So for 10 mins, that's going to be 3 times 2, giving me a Poisson of 6. Okay, all you've got to do, put this on your calculator, and you'll get 0.446 to 3 significant figures. So there we have it. So that's that question done. Quite a quick one overall. The Poisson distribution, to be fair, isn't too difficult. It gets a little bit harder with hypothesis testing, but I'm not covering this in this video specifically because that is in, I think it's chapter 4, I believe. It's covered in the hypothesis testing chapter, so I won't be doing any of them for this video. So we get to this one here. And this is taken from the old exam. So this was taken off the old Edexcel further math spec, so it was Edexcel S2. So it was June 2008, I can't read, question 3. So if you want to look at the paper, be sure to check it out. It is a mix of some of the old Edexcel, the current Edexcel A-level maths stats area, further stats 1 and further stats 2. So you'll see a mix of questions on there. So question 3A. It just says state two conditions under which a Poisson distribution is a suitable model to use in a statistical work. So what are the two conditions that we need to be thinking about? Well, one condition is that the events occur at a constant rate. Like we said in the beginning of this video, it's always under a constant time frame, so every 10 minutes, every hour, every day, something like that. So events occur at a constant rate. Okay, so that's one point. My next point, I'm just going to say that the events occur independently. Okay, so one event doesn't affect the other event. So events occur independently. Okay, so them are just the 2 points that we need to make there. So the events occur at a constant rate, and the events occur independently. And then part B, we're told that the number of cars passing an observation point in a 10-minute interval is modelled by a Poisson distribution with mean 1. So if we say x, modelled with a Poisson distribution with a mean of 1. So this is for 10 mins. So in the question, it's a 60-minute period. So to get from 10 minutes to 60 minutes, we need to times that by 6. Okay, so that'll be x is modelled with a Poisson of 6. Okay, so just being able to adjust this is the key skill here. You can do this really straightforward. So the probability that there are exactly 4 cars, that's just going to be the probability that x is equal to 4. But if you do this on your calculator, you'll just get 0.134. Okay, so that's simply all it is for that one. And then the second one, there's at least 5 cars. So remember, when you see the words at least, it's greater than or equal to. So probability that x is greater than or equal to 5. Now remember, if it's greater than or equal to, we need to subtract everything less than it, so we can get that upper value. So 1 minus the probability that x is less than or equal to 4. Plug this in on your calculator using this mean value here of 6, and this will be 1 minus 0.2851. Do that on your calculator, and you get 0.715. Okay, and that's simply all it is. So nice and easy. That was quite a nice, easy question. If I'd have got that on my exam, I'd have been very happy. So let's move on to the next one. I think this is the last question here today. So this is Jan 2013, again off the old Edexcel further maths spec. So S2, question 1. Another question again in which it wants kind of a bit more detail. So 2 conditions, and we know I want 2 because look at the marks. 2 marks, 2 points. Okay, so you use the marks as a guide a lot of the time. It's kind of a big hint of how many points you need to give. So I need 2 points for this. So what I'm going to say here is that one of them is that I have a large n value. So when we're approximating to the binomial, we need a large n value. Large n value. And my other point that I need to make is that we have a small p value, so a small probability, so small p values. Okay. So them are the conditions which we can use the Poisson distribution as an approximation to the binomial. Now in part B, it actually wants us to carry out an approximation. So this is again something you'll be assessed on, being able to approximate from a Poisson distribution to a binomial. So we're told the probability of any one letter being delivered to the wrong house is 0.01. So that satisfies that. It's a small p-value, a p-value of 1%. So we have a small p. We have a large n here, 1,000. So we know this is a good approximation. So if I write this down, so this is modelled as a binomial here, with n being 1,000 and my p being 0.01. Well, to approximate this, remember, all I do is do n times p, so np. That gives me my lambda value. So lambda is equal to np. So if we say y is distributed with a Poisson of 1,000, so my n times my p, 0.01. Do this on your calculator, and what you'll get is that y is modelled with a Poisson, and this value here, my mean, is 10. Okay. Now we're looking for the probability that Peter delivers at least 4 letters to the wrong case. So at least, again, just like we said with the last one, that means greater than or equal to. So we're looking for the probability that x is greater than or equal to 4. And if you ever get greater than or equal, like I said, we're always looking to subtract the lower off, just so we can get that upper value. So probability that x is less than or equal to 3. Now you just need to use your calculator using this distribution here. So using this distribution, I want to know what the probability that x is less than or equal to 3. Well, if you do this on your calculator, what you get is 1 minus 0.0103. And if you put that into your calculator again, you're going to get 0.9897. Okay, so quite a large probability. So Peter's not very good at delivering letters. And that's the 4 decimal places as well, so 4 decimal places. Okay, so yeah, like we said, Peter's not very good at delivering the letters. But there we have it, so that's the final question for this video. I'm going to do another video probably on Poisson Distribution as well, looking at some trickier questions. But hopefully that's been a nice introduction to it. Nothing too tricky, I don't think. If it's helped, be sure to subscribe, like the video, leave me any comments, feedback, anything down below. It's very much appreciated, guys.